honor to speak to you today. I'm going to speak about the coolest technology of them all, but also the least visible, software. It's all about scale. The scaling of Moore's law is in the number of transistors. The scaling of software is in the complexity of the system, in the capabilities that it can manifest. The question is, how do you scale complexity? That's the software story. Software is like writing. This is a comparison that makes sense not just because we're here in this museum of journalism. It's because software is a symbolic medium, and it can describe great complexity and nuance. It is trivial to reproduce, but it requires special talent to design it well. As the storyline gets more complex and innovative, the design task becomes more difficult. And it is also difficult to validate. We must succeed both with fact-checking, so to speak, and also with assuring airtight reasoning. It's singularly difficult to become fully confident in appraisals of its quality. Stay tuned. Cybersecurity is next. But Robert Mueller said just a few days ago that cybersecurity is soon to become the #1 focus of attention for the FBI. Despite all of this, software has huge economic impact. One could say that while it is weightless, it is also of enormous gravity. Indeed, software has become the building material of choice. Half of the functional features of a modern automobile are now manifest in software. A recent headline asserted, for example, that Ford has become a software company. The Ford Motor Company has become a software company. More than 80% of the functional features of a modern military fighter jet, this is an image of an F-35, are manifest in software. A commercial jet was described some years ago as software with wings. We've heard some economic representations. They assert that in the last decade or so, fully 20% of the nation's economic growth is accounted for by networking and IT industries. In Europe, similar studies suggest 25% of overall growth, 40 to 60% of the increase in productivity, all due to IT, which is actually a relatively much smaller industry if you look at its share of GDP. The role of software has become pivotal in industries ranging from financial services and healthcare to logistics, transportation, and utilities. It is one of the greatest contributors to the military force multiplier provided by advanced technology. It is the prime building material for our critical infrastructure and for our national security systems. Software does not stand alone. The economic ecosystems, the socio-technical fabric, is extremely complex. This is the VA healthcare system, the VISTA system. This complexity is because we don't only manifest features in software, we do two other things. First, we use software as a way to link things together. Supply chains, customer relationships, intelligence, assets, and analysts, our personal financial lives, manufacturing, inventory, and logistics. Second, we use software as a way to increase agility. The Facebook experience for 800 million users, the third largest country, can change overnight through the work of a few programmers. Military systems and infrastructural systems have the potential to adapt rapidly to changing threats and shifting conditions. The potential. Success in implementing electronic health records, shown here, requires all of these attributes. These are three special characteristics of software, but there's one characteristic that is more special than the others. This is the fundamental unboundedness of software. Let me explain. We are seeing and will continue to see a continuous gain in the scale of software. That is the extent of complexity, the degree of interlinking, the astonishing agility. Is this a consequence of Moore's law, the transistors on a chip image that we saw earlier? No. It is enabled by Moore's law, but it is not a consequence. That's because the scaling in software is a scaling in design complexity. It's a human outcome, so to speak. But if you draw the human version of the Moore's Law curve, it's a flat line. Humans aren't getting any smarter, unless we look at time spans on the orders of millennia. So what's happening is that we're getting better in 4 areas. Languages, advanced object-oriented and functional languages, domain-specific languages, and so on. Models, architectural models, design patterns, inline specifications, all to support analysis, understanding, and evaluation. Practices, agile, small teams, incremental, iterative development, measurement, quality practices. Tools for developers, for teams, for assurance. And there's a reinforcement in this process. Improvements in models and practices find their way into languages and tools. The boundary between software management and software technology continues to shift. In other words, with respect to that writing analogy, we're in the news museum, metaphors of types, of objects, of parallelism, of high-order functions for mathematics, map-reduce. All of these find their way into the models, and then they eventually find their way into the languages and libraries. And the progression continues. Next, machine learning, security policies. So why am I telling you all this? Because these 4 areas, these are the nitered special sauce. I'm going to mention 2 examples so you'll see how subtle the story is, but it's essential to understand the story. First, in the 1990s, Microsoft found out that those blue screens, anybody had a blue screen lately? Right? Those blue screens, 85% of them were caused by protocol violations in device driver code. Researchers at Microsoft saw that they could apply a deep technology, model checking, to that device driver code to assess consistency of the implementation of in the code and the finite state models that were the intended models to support the protocol. Model checking is like running trillions of test cases all at once. That's the idea. Where did model checking come from? Research done 10 years earlier, funded by NSF and DARPA. Ed Clark's Turing Award. Now, all those college sophomores, all your students, undergraduates, on their summer jobs, writing device driver code for the next little gizmo to plug into your USB port, right? They're using this tool that readily assures that particular dimension of safety. Second example. I've got it. What's inside this iPhone? Right? The operating system, the Mac OS, was funded by DARPA in the 1980s. Vint mentioned the Strategic Computing Program. That was the source of sponsorship for that. Why did they sponsor it? For distributed computing, for high-performance computing, for security, a whole range of issues. Its first commercial appearance was in that Next computer. Do you remember those black cubes? Now it's in your phone. So if we trace these software technologies to their roots, and the pathways can be quite complex, very often you find NIDARD-funded researchers and students. Okay? It's a complex ecosystem. That's my point. Now I want to digress for a moment on open source. That's because these 4 areas of improvement have enabled tremendous success in the top open source projects, the projects that are widely adopted, including in critical infrastructure. The good reasons why IBM, for example, has put more than $1 billion into supporting the Linux ecosystem, and why Apache is the most widely adopted web server. The open source projects that are successful are exceptionally rigorous regarding process practices, tooling, and people. They operate in an economic role that's analogous to a consortium. It's most definitely not about liberating software, about strange IP ideas, about anarchic management, or other such notions. Open source has become an economic phenomenon related to cost, risk, and control. So these 4 areas of improvement also enable richer sourcing practices, more reuse, and richer supply chains. Sourcing, we used to think that sourcing was driven by cost, but it's actually driven by access to expertise and by flexibility, organizational agility, access to already built components, products, and infrastructure, and by the realities of human geography. It's easier to go to the talent than to bring the talent to us, and our technologies enable that, so there's an amplification. If I may make a plug, that's why Google, Disney, Apple, Intel, and others have come to Pittsburgh, not just because of our great weather. So I also want to mention the extent and importance, the necessity of reuse in software. Reuse. The most evident, this is most evident and most obvious in the socio-technical ecosystems that now dominate our landscape. Think about iOS, Android for mobile devices, the web services ecosystems, ASP.NET, Java EE, and so on, ERP, SCM, and CRM infrastructures for the enterprise, SAP and Oracle, SCADA infrastructure for utilities, MapReduce and big data infrastructure. MapReduce Hadoop is a framework, and you just slot tiny bits of code into that framework and you get amazing big data analytics. Cloud services, virtualization infrastructure, all these are enabled by these technical advances, these same four areas. So it's important to recognize just how much technical and economic leverage we get. It's also important to recognize how much of this leadership in these ecosystems is here in the U.S. and how much this empowers our industry in world markets, not to mention our national security leadership. But it's well understood by all of us that we are in an increasingly competitive landscape. Success derives from the right mix of technical and cultural factors. And this brings me back to the idea of unboundedness. This is the sourcing slide that I missed. But that picture is the sourcing for Linux contributed code around the world, compiled by Red Hat. The laws of physics, which limit what we can do with physical building materials, have relatively less influence on the symbol manipulation that is at the heart of software. It's more about our ability to leverage our finite, bounded human intelligence through advances in these four critical areas. Through this reuse. Reuse is a tricky word because it implies sort of recycled code, but it's much more about finding the right amount of generality, where and how much. Enough, but not too much. So I drove in from Pittsburgh to be here today. It's a very pleasant drive. The steel industry that used to dominate our landscape economically, visually, culturally, has now gone mostly overseas. We have recovered and gotten stronger with a robust economy of eds and meds. This was a disruptive change, but we're now okay. In fact, more than okay. And I want to tell you, though, that with the loss of software leadership, we will not recover and grow stronger. We will not be okay. This is a strong statement. The reason I make it is this: future software improvements will not diminish into a few percentage points of cost, timeliness, or quality. They're going to emerge at a rate and significance that, if anything, is going to be greater than before, greater than the last 60 years. There was a paper published in 1958 by John Backus, who many of us knew. It was about one of the first compilers for the Fortran language, a bit of software virtuosity in its time. Its title was Automatic Programming. What did this mean? It meant that the mathematical abstractions embodied in that language were so close to pure mathematical thought that the mathematicians who previously relied on all these programmers, we're all programmers in here, the intermediation of programmers between themselves and the computer could now express their mathematical thoughts directly to the computers, and Fortran would do the rest. Automatic programming. But Fortran had these wonderful built-in ideas of integers and real numbers, arrays of these things, limitations. It was well suited. Well, what happened then is characteristic of our entire history and will characterize our history going forward. Somebody got the idea of manipulating text. Search in a set of documents, typesetting, and the text needed to be represented as numbers and arrays. The mathematicians had to keep remembering what was what. So suddenly things got complex all over again, and so the next generation of languages incorporated new abstractions, right, that facilitated the text manipulation, but then our ambitions increased again. And so the magic is, and the magic of software, and the unboundedness of software, is this is a cycle that can continuously repeat itself indefinitely into the future. Nobody I know sees a limit or any kind of plateau in the future on the time scale of decades. This pattern, this cycle of innovation is the characteristic of software. And the most fundamental advances in this area have come from long-sighted investment in federal R&D programs. Less emphasis on appropriability, more emphasis on broad impact, raising the playing field. So I just want to close with a comment about NITRD. NITRD enables these breakthrough advances, these technical game changers. This is the 1992 report, the first Blue Book that came out. Many people in here, I was one of them, were part of the process of creating this thing. Okay? So let us keep in mind that this continued national leadership that we enjoy in this industry is not an accident. It's the result of this historical symbiosis of federal basic research manifest in these programs, academic research, educational programs, industry innovation. We're only getting started with software. We're only getting started with software. Thank you very much.
You talked about software as an enabler of change, which implies time, and it becomes more important over time. What I didn't hear you mention was the implications of that change, that in fact change can have a multiplier effect on the impact of scale and complexity.
Yes.
If you have anything to say about that.
Yeah, that was the cycle whereby we develop new metaphors, new ways of thinking about our code. We manifest them in formal notations of models that allow us to represent our concepts about the code, our intentions about the system, and eventually those models and concepts find their way into the next generation of language design. First-class typing is an example in all the modern languages, or not the dynamic languages, but in all the modern languages.